This is just an introduction for stereochemistry. This is again one of those fundamental topics that you will learn now and you will always keep using it in future. So make sure you learn it well. So what is stereochemistry? Stereo has something to do with the left and right, just like you would have audio. So in audio, you have a left stereo and a right stereo. So the same thing happens here, is you have a left and a right thing. Okay, so how does that happen? Okay, why is it that compounds can have a left and a right issue, okay, or handedness, or kind of an issue? So this kind of an issue arises when a carbon has four different groups, okay, and that kind of a carbon is going to show chirality. Okay, so that's the property that it exhibits. Again, this is a property of any carbon that has four different groups. So what does it mean that it shows chirality then? So chirality means that if you take a group or if you take a molecule which has a carbon that has four different groups around it, and you show a mirror to it, then you'll have the mirror image of that molecule. And if you take that mirror image out of the mirror and try to superimpose it on the first one, on the original molecule, it's not going to happen. Okay, so carbon is a tetrahedral, don't forget. And because of that reason, okay, the two molecules are not going to be able to superimpose. That is called chirality. And again, why does chirality happen? Only because carbon has four different groups and carbon is a tetrahedral. All right, so basically that is chirality. Okay, so let's just say this again. Chirality is when the two mirror images are non-superimposable on each other. When the tetrahedral carbon has four different groups, that's when we say that we have a chiral center. Okay, again, four different groups. And this carbon here is a tetrahedral. This is an important thing too. A tetrahedral carbon is an sp3 carbon. An sp2 carbon will not be chiral. Okay, because it has a double bond and the shape is different. All right, so a tetrahedral carbon has a tetrahedral shape and that is going to have a chiral center. There are exceptions, but right now we don't have to worry about that. Okay, so then the mirror image pair of those compounds, okay, remember the mirror image we just talked about in the previous slide, those are called enantiomers. All right, so there's a specific name for the non-superimposable mirror images. So the only thing that is different about the two molecules is how they rotate the plane polarized light. Okay, what is plane polarized light? We'll talk about that in the next slide. But really, when you're looking at a molecule that is a mirror image, okay, of each other, then really how do you tell the difference between the two? Okay, it's going to be a very hard thing to do. Okay, is tell the difference between, because they will have the same properties, they might have the same reactivities. So how do you tell that you even have a pair of enantiomers? And this was really a hard thing to do eventually. Okay, so we will talk about how it came about to be, but in any case, the only difference between the two molecules is how they rotate the plane polarized light. And they rotated in equal and opposite directions. So if one or the original molecule is rotating it plus 30 degrees, then the mirror image is minus 30 degrees. Okay, so that's equal and in opposite direction. So one of the things that you have to be very careful about as you're learning chirality, as you're learning stereochemistry, is how to draw molecules. So I have not been emphasizing it too much, okay, until now, but you are going to have to draw now in 3D. Okay, so which means that you have to indicate the bonds that are in the plane, which is this plane line over here. You have to indicate what bond is coming out of the plane, which is this dark wedge. And then you have to indicate what is going behind the plane, which is the dash line, okay, which is the hydrogen over here. So since carbon is a tetrahedral, it is not a planar molecule. So you have to indicate what groups are where. So always there are going to be two groups in one direction. So whether they are going in the plane or behind the plane or whatever it is. Okay, so you'll have two groups in the same direction and then two going in opposite directions. Okay, so we will learn more about this, how to draw these molecules a little bit more later on. But please remember, In stereochemistry, it's really important to draw 3D molecules because you have to indicate whether the group is coming out at you or going behind, going left or going right, because we're talking mirror images. So the difference between them is very minute, okay? So here are some representations of molecules. So for example, if you look at these two over here, these two are pretty much the same, okay? Because this is going to the front. Excuse me, actually, these two, this is a flip, okay, of this one. So, but this is the mirror image, okay, that you will draw for each of them, okay, because these are the enantiomers. In one, the OH group is coming out of the plane, and the other one is going behind the plane because that's the mirror image, okay. So that's how we'll do. We'll practice more. So here are some other enantiomers also. So just the 3D structures, just appreciate how to draw in a 3D because you have to do it. If you don't, then it's hard to tell which group is going where. Okay, so if you switch chlorine with hydrogen, then suddenly you have a different enantiomer. Okay, so you have to be careful. So these two images are mirror images of each other, and it's a nice practice to do. Okay, so just draw a molecule and draw the mirror image of it. So you can draw all the wedges and the dashed lines. Okay, so this is for a straight molecule. You can draw it for cyclic also. Okay, so in the cyclic, these two lines over here, they are in the plane. What is not visible to you is the hydrogen, which is going behind, okay, right now. And it's a little problem of organic chemistry, the case of the invisible hydrogen, but that's always there. Okay, so we know it's there, but it's going behind. Okay. So here, you should figure out how many chiral centers you have in this compound. And the best way to identify a chiral center is to look at each of the carbons, okay, and then see if it has 4 different groups attached to it. That's it. If it doesn't, it's not. Okay, that's how simple it is. So this one actually has a lot of chiral centers, okay, because you can see, first of all, there is the 3D structures going on too, but that's not sufficient. Okay, so you still have to take a look at it and then identify if there are 4 different groups attached. Okay, so again, this carbon is not going to be chiral because this is a double bonded. This carbon can be chiral. So what are the groups on this carbon? You have a CH3, a methyl group coming out of here. You have a carbon with a double bond. You have a hydrogen, and then you have a carbon with a hydrogen and an OH. So yeah, you have 4 different groups attached over here. So that's going to be chiral. Okay. This carbon here is not going to be chiral because it has a CH3. It has all of this carbon, which has a hydrogen and oxygen and carbon attached to it. But this carbon also has 2 hydrogens. So if you have 2 hydrogens, it means you have the same groups, and so that's not going to be chiral. Well, neither is CH3, okay, because it has 3 of the same groups. So anyhow, go through it, okay, and then figure it out, and just wait a little bit, pause this, and then you can see the answers, okay, because it's all given to you. So Pasteur's discovery of enantiomer. Pasteur was the first one to discover enantiomers, although he didn't really pursue it a whole lot, but he was the first one to find out about enantiomers. And the way he figured it out was using tartaric acid. So Louis Pasteur, we all know him from pasteurized milk, of course, but Louis Pasteur was a consultant, sort of, for a winery, and the winery was having issues with tartaric acid. Tartaric acid is produced during winemaking, actually, and so they wanted some help with the tartaric acid. So when Pasteur took the tartaric acids that were crystals, and he looked at them under the microscope, he saw that there were 2 crystal shapes. And he couldn't figure out why there were 2 crystal shapes, okay, for tartaric acid. So very painstakingly, he actually decided to separate them out. Okay, so under the microscope, he separated out the crystals that were facing one way versus the other way. But then if you look at the crystals, and this is what he did, is that they were exactly mirror images of each other. And so then when he put them through the optical rotation, he figured out, oh, they're rotating the light, but in equal and opposite direction. So this was kind of how the study of enantiomers got started, but nothing happened for another 50, 60 years. Okay, so it took a while before it came back into play again, because there are so many other issues, okay, with enantiomers. So we will talk about it step by step, but nothing happened, okay, for a long time until the 1940s then. But in any case, so here is the structure of tartaric acid. So you understand that there are chiral centers here. This is the chiral center. This is also a chiral center. So there are two chiral centers in tartaric acid. So this is kind of how stereochemistry got started. So let's talk about optical activity now, okay, because we've been talking about optical rotation. So in any case, this is what we call general light, which is not polarized in any way and it's just going in all directions. So a plain polarized light would be to taking one of these rays and passing it through a slit. So you get only light in one plane, going in one plane, okay. So this is how it's going. So this is the light, okay, that is used for the optical rotation determination. I'll show you the instrument in just a second. So you take the plane polarized light, add it to the instrument, and then have the compound in there as well. And once the light passes through the compound, then you will get the rotation. Now, two words to note over here. Dextrorotatory means that the rotation of the light is clockwise or going towards the right, and anti-clockwise is levorotatory. Okay, so dextrorotatory is small d, levorotatory is small l. It's really important that you know that it's a small d and a small l, because in organic chemistry and biochemistry, you will also encounter capital D and capital L. Okay, so you got to be careful that you don't mix up your capitalized letter and small case letters over here. Okay, so those two words you're going to learn. The rotation is measured in alpha, which is, it's a degree thing. So that's all. Okay, not so critical over here. These two words are going to be critical for us. So here is the polarimeter. Now we don't have a polarimeter in our lab, but if one has a polarimeter, one works with chiral compounds, then you have to have a polarimeter, because this is one of those physical properties like a melting point, boiling point, that you have to figure out, okay, is what is the optical rotation of this molecule. So in any case, this is a polarimeter. So here is the light coming through, passing through a slit, and then here comes the plane polarized light. The sample is coming through here and the light gets rotated, and you see what the rotation is going to be. Okay, so it's just an instrument that is used to figure out the rotation, whether it's D or L, and the value. So then comes the specific rotation. Specific rotation is going to be for an optically pure compound. So it cannot be for a mixture. It's not a good idea to do that, because if you have a mixture, then your rotation is not going to be clear, right? Because you don't know if the other enantiomer is messing up your rotations in there, because remember, the enantiomer is opposite direction. So in any case, this is a specific rotation. Now I usually don't do too much of specific rotation calculations in my lecture, but you have the formula here in case you ever have to calculate the specific rotation in any kind of future class that you want. And this one here is lactic acid. So you can see here that the plus over here, the plus, by the way, is also an indicator of D, dextrorotatory. The negative, the minus, is also an indicator of L, which is levorotatory. So they have two indicators. Okay, so D plus or L minus. You can use either of those. Okay, so either use D or plus. That's what I meant. So in any case, here are their optical rotations, and you can see this is equal in opposite direction, as these two are enantiomers. So a little bit more over here for specific rotations. Now, later on, we are going to be talking about R and S designations, because you have to indicate which enantiomer you're talking about. So we're going to learn about R and S in the next PowerPoint. So, but I just want you to know in advance that there's absolutely no relationship between optical rotation and R and S. Okay, so you make a note of it, and then when we get there, you can remember this. Okay, so just make sure that the compound has to be chiral to be optical active. If it is not chiral, it's not going to be optically active. Okay, and so that's an important thing. You can't predict what the rotation is going to be, because it's a property. It's like melting points. You can say it's high, but you don't know how high, okay, or the number. So that's something you have to be careful of. Now, one of the things and one of the reasons why it's so hard to study enantiomers is because of this reason, a racemic mixture. Racemic mixture is a 1-to-1 mixture of the enantiomers. Equal mixture, 50-50 mixture, okay, of the enantiomers. So if you have equal of one enantiomer and the other one, then you do not see any optical rotation. So unless you know the structure of the compound and you say, okay, I know I have chiral centers in here, you will never be able to study the optical rotation, okay, of that molecule. So racemic mixture is a mixture of the D and the L, okay, in there. We're not talking RNS yet, okay? We're going to talk about that later, but you can also say RNS, okay, in case you want to start preparing in your mind, okay, for that. So an equal mixture of D and L is called a racemic mixture, or an equal mixture of RNS is called racemic mixture. And a racemic mixture is not going to show you any optical rotation because it is equal in an opposite direction for each of them. Okay, so generally you can designate that as plus minus, but really there is no optical rotation, not because of no chirality, but because of equal mixture. So before I go on to talk about other things like RNS and whatnot, I just want to mention to you the importance of chirality and the importance of stereochemistry. We have 20 amino acids in our body, which make up all the proteins that we have in our body. And all the amino acids are very specific in their chirality. If they are not specific in their chirality, then we're going to have issues, okay? Because we can have only certain kinds of chirality in our body. At this point, it's not important for us to know what kind, but I'm just telling you, okay, that you need to have very specific enantiomers in your body. Otherwise, it's not going to work out, okay? And amino acids, they have a chiral center. Most of them do. There are 20 amino acids, and I think about 17 or 18 of them have a chiral center. Okay, so, oh, here we go. In 19 of the 20, the alpha carbon is chiral. So there's only one that doesn't have a chiral center, and I think that is the alanine or something like that, the smallest amino acid. But then you can see that most of them have R configuration. We'll talk about R in the next one, in the next PowerPoint, and then one has S configuration. So you will learn about what that really means. Okay, so at this point, it's not important. Just know that they are going to be mirror images. R and S are mirror images of each other. So, but amino acids have very specific configurations. Okay, configurations meaning which direction the four groups are going, okay, around the carbon. So carbon is the chiral center, the carbon here, that is the chiral center. So the R and the S tell you exactly how these four groups are attached. So in the amino acids, it's kind of very specific, okay, how they're attached. And so it becomes really important for us to learn about these things, okay, about R and S configuration. The same thing happens in carbohydrates also. So there is a little bit more about chirality in the biological world, because amino acids is one thing, then there's carbohydrate, and then there are a lot of enzymes which are made of amino acids. And it's a huge thing for us. And it's not just the fact that amino acids are chiral. Okay, you can read the whole thing over here. Okay, you can read the whole slide. I'm not going to read the whole thing here. But it's not just that the proteins or the enzymes, they are chiral. It's also about drug interactions. Okay, so this right here at the bottom, this talks a little bit about drug interaction. And here it is explained a little bit more. Okay, so each enzyme or each binding site can bind only to a very specific thing. And if it is not specific to that, it's not going to bind. Okay, and so drugs, for example, when we make drugs or medicines, we make them in a very specific way. In some binding sites, it doesn't really matter. They're flexible, they can take whatever. But some binding sites are going to be very specific, that they will take only one enantiomer and not the other enantiomer, just because of the way it is. Okay, and that's why some drugs work, some drugs don't, because of these binding sites. So it's a very important thing that, we have to study these chiralities, all right? It's a very fundamental thing. So in this PowerPoint, there really was not a whole lot, okay, going on. I just wanted to introduce to you what a chiral center is, what chirality is, what an enantiomer is, and then dextrorotatory and levorotatory. If you don't remember anything about the biological world, it's okay. Just know that stereochemistry is a very fundamental thing and it's really important for everything that we do.